A pleasant day to you, my dear students in BS Agri first year. I am welcoming you to our lesson 1 in organic chemistry, the introduction to organic chemistry. Are you familiar with the following terms, or have you heard of the following terms? Organic fertilizer, organic farming, organic vegetables. I know that you are very familiar of these terms. So, what does the word or the term organic mean? The word organic was originally used by 18th century chemists to describe substances obtained from living sources. Okay, when we say organic, it is a substance or any substance that was actually derived or originally derived or obtained from a living sources or from the living organisms. These chemists believe that nature possesses a certain vital force and that only living things could produce organic compounds. So they believe, or these chemists believe, that it is only from the living organisms that an organic compounds can produce. But this romantic notion or this belief was actually disproved in 1828 by Friedrich Wöhler. He is a German chemist who prepared urea. I know you are familiar with that, urea. It is an organic compound from the reaction between the inorganic compounds lead cyanate and aqueous ammonia. So, that belief of the chemist before that the organic substance or organic compounds can obtain only from living sources was disproved by Friedrich Wöhler in 1828 because he was able to create or to produce an organic compound, urea, from inorganic substances. At present, we have over 14 million synthetic or artificially prepared in laboratory and natural, which means present in nature, organic compounds. So we have millions of organic compounds today. And it is not only, or those organic compounds are not only obtained from a natural living sources, but also most of them can be produced inside the laboratory, and that is why they are called synthetic or artificially prepared organic compounds. This number is significantly greater than the 100,000 or so known in organic compounds. Modern day definition of organic compounds, generally it refers to any chemical compounds that contain carbon and hydrogen bonds. Due to carbon's ability to catenate, meaning to form chains with other carbon atoms, millions of organic compounds are known. So what is organic chemistry? It is the study of properties, reactions, and synthesis of organic compounds. Before digging deeper into the study of organic chemistry, let us review some of the fundamental concepts of chemistry you learned in your general chemistry in high school. Let's see if you can still recall those fundamental concepts, because those are important foundation, basic foundation that you need to acquire, or at least you need to recall in order for you to understand, to fully understand our lesson in organic chemistry. So come on, let us go back to some of those concepts. We learned in high school that ionic compounds are formed by the transfer of valence electron or electrons from metal atom to non-metal atom. That is called ionic bonding. And also we have what we call the covalent compounds. So these are formed by the sharing of valence electron of two or more non-metal atoms, and that is covalent bonding. So we have two types of compounds here. We have the ionic and we have the covalent compounds, and they are different, because the difference of these two is based on how they are formed. So in ionic, it is formed by the sharing, the transfer rather, of valence electron, while in covalent, it is formed by the sharing of valence electron. Another thing is, in the ionic compounds actually are formed by the metal and the non-metal elements, while the covalent compounds are formed by the combination of two non-metal atoms by sharing their valence electron. So organic compounds are compounds that are covalent compounds because they are formed by the sharing of valence electron between two or more non-metal atoms. That's why it's important for us to try to recall these fundamental concepts. Later, we will understand that the formation of these organic compounds involves the covalent bonding, meaning the sharing of valence electrons. So how did it happen? So let us try to recall these terms. So we have the octet rule. The octet rule meaning the rule of 8. Octet from the Greek prefix octa meaning 8. So that's why it is also called the rule of 8. Or it is also called the stability rule. So it states that an atom, except hydrogen, tends to form bonds until it is surrounded by 8 valence electrons. So octet rule, also called the rule of 8 or the stability rule. Now, I'm going to ask you a question. The word stable. Now, if I'm going to ask you personal question that goes like this. Are you a stable person? Are you a stable individual? Some of you might answer, no sir, I am not yet a stable person or individual because I don't have a permanent job. Yeah, that's correct. Do you have a stable job? No? So what does the stable mean? For a person to become stable, maybe the criteria for a person to become stable is usually a permanent job or a business that was actually already established, right? But in an atom, the stability of an atom relies on the number of valence electron. An atom is said to be stable if it has a minimum requirement is for the atom to have two electrons in the first main energy level and 8 electrons in the last or outermost energy level. Okay? So the requirement for an atom to become stable, it should have at least 2 electrons, or it should have 2 electrons in the first energy level and 8 electrons in the last main energy level. Now, the electrons found in the last main energy level or the outermost energy level is called the valence electron or electrons. Take note of this because this term we will continuously or we will consistently use this term here. The valence electron. Valence electron is very important, or it has a very important role in chemical reaction because these electrons are responsible, or they are responsible in compound formation. In the compound formation, they are the ones involved, or they are the ones interact with other atoms, with the valence electron of the other atoms in order to form a covalent compounds. So take note, valence electron has a very important role in a chemical reactions because they are the ones reacting with the valence electron of the other atoms. In order to become stable, an atom might gain or lose its valence electron. So a metal element like sodium loses its one valence electron and transfer it to chlorine or the Cl with 7 valence electrons to form sodium chloride or NaCl. Sodium or Na becomes a positive ion and Cl or the chlorine becomes the negative ion. This process is called ionic bonding. So the combination of the sodium atom and the chlorine atom, sodium is the metal, chlorine is the non-metal. When they combine together to form a compound, they form an ionic compound called sodium chloride. So sodium chloride is popularly known as the table salt or asin. The ones we are using when we cook food in our kitchen. It is an example of ionic compound. So in figure 1, we can see how the ionic bond formation of sodium chloride. So we can see here that the sodium has an atomic number of 11. So Cl, or the chlorine, has atomic number of 17. We can find that, or we can see that in our periodic table. Anyway, this is also a requirement in your subject, in your organic chemistry, that you must have your own a copy of a periodic table. I am going to check that. Maybe you can post that in the picture of your periodic table, can be posted in our group or in our Google Classroom for checking. So let's go back to the ionic bond formation of sodium and chlorine to form sodium chloride. So sodium has an atomic number of 11. You can see here that we have main energy level 1, 2, and 3. For the distribution of the number of electrons of sodium, the sodium which has electrons of 11 distributed in the different main energy levels. So we have 2 electrons in the first energy level. We have 8 electrons in the second energy level. And we have 1 electron in the last energy level. So, in sodium, we have a valence electron of 1. Okay? Now, for the Cl, we have atomic number 17. So, since we have 17 atomic number, we have also 17 electrons in chlorine. So, distributed in the different main energy level, you can see that in the first main energy level, we have 2. That's the maximum capacity of the first energy level. The second energy level, we have 8. And for the third, we have 7. Okay? That makes, or it gives us a 17 atomic number. Now, the valence electron of chlorine is how many? 7. We have 7 valence electron for chlorine, and we have 1 valence electron for the sodium. So, as you can see here in the illustration, the sodium atom, or the Na, will lose its 1 valence electron. Another term for lose is to remove. Remove 1 valence electron. So in this process, sodium will give up or will remove the 1 valence electron and give it or transfer it to the 7 valence electron of Cl. Okay? In that process, we can see that the sodium losing 1 valence electron, while the chlorine gains 1 valence electron. Now, below you can see that the sodium that loses 1 valence electron carries a charge of positive, while chlorine carries a charge of a negative. So you can also see that what happens to the energy level of sodium and chlorine is that for the sodium we have 2, 8, and 8 in between the sodium and chlorine, and 2, 8, and 8 also for the sodium. The sodium and chlorine, they both have 8 valence electron between them. So notice that both sodium and chlorine become stable because the sodium transferred its 1 valence electron and give it or transferred it to the 7 valence electron of chlorine, thereby forming 8 valence electrons between them. So what happened to them is, because the sodium give up its one valence electron and the chlorine accept or gain that valence electron and add that one valence electron from sodium to the 7 valence electron of chlorine, they have now 8 valence electron between them. That's why sodium and chlorine become stable, or they gain stability because they have already 8 valence electron between them. In the process, sodium that loses one valence electron carries a charge of positive or Na positive, while chlorine that gains one valence electron carries a charge of negative or Cl negative. An atom that carries a positive or a negative charge is called ion. So, positive ion is called cation and negative ion is called anion. So, which is cation or anion in this example? Sodium or chlorine? Another way for atom to become stable is to share its valence electron with other atoms. So that is called sharing of valence electron. This sharing of valence electrons between two or more nonmetal atoms is called covalent bonding. To fully understand how covalent bonding happens, let us first talk about Lewis dot symbol. Lewis dot symbol consists of the symbol of an element and one dot for its valence electron in an atom of the element. So, it was formulated by American chemist Gilbert Newton Lewis in 1875 to 1946. Valence electron is represented by dot. So here we can see the Lewis dot symbol of the different elements in the main group of elements from group 1A to group 8 of our periodic table. You can see that for the group 1A, all the elements in the group 1A has one dot, meaning they all have one valence electron. And that valence electron is represented by the dot. So the dot represents the valence electron. For the group 2, you can see from Be, beryllium to radon, it has 2 valence electron represented by 2 dots. For the group 3, we have the 3 dots. Group 4, 4 dots. Group 5, 6 also have 6 dots. 7 have 7 dots. And 8 has 8 dots, except for the helium. So the formation of covalent compound, let's have an example. Let us show how the covalent bond formation of hydrochloric acid or HCl, that is a combination of the hydrogen and the element chlorine. So you can see here that hydrogen belongs to group 1, has 1 dot, meaning it has 1 valence electron. While chlorine belongs to group 7, has 7 dots, meaning it has 7 valence electron. Now in the process, you can see that hydrogen, in order for the hydrogen to become stable, it must have at least 2 valence electron. If you can still recall, we said that an atom to become stable must have at least a minimum requirements of having 2 valence electron in the first energy level. And because hydrogen has only 1 valence electron, and so this atom of hydrogen needs an additional 1 valence electron to become stable. Well, for the chlorine has a valence electron of 7, and in order to become stable, it needs an additional 1 valence electron. So, the mechanism here is not transfer, but sharing. Sharing the valence electron of 2 nonmetal atoms for them to attain the stability or the octet rule or the rule of 8. Here, we can see that hydrogen shared with 1 valence electron of chlorine, while chlorine also shared with the 1 valence electron of hydrogen, thereby attaining the stability of having 8 valence electron. The hydrogen attains stability by having 2 electrons, and the Cl or the chlorine becomes stable by having 8 valence electron because of sharing. No. This is actually a very simple illustration of, for example, you want to drink soft drinks or soft drinks because of the hot climate or hot temperature during the day, but you don't have enough money to buy 1.5 liter of soft drinks, say for example a Coca-Cola. Now, because you don't have enough money to buy, what we usually do is to share our money, to chip in. That's the term, to chip in, or in Tagalog that's patak-patak, right? So one of your friend will or might give 20 pesos, the other will chip in 5 pesos until such time that you can already raise fund or raise money to buy the 1.5 liter of Coca-Cola. And that is sharing. Sharing to attain or to achieve a common goal. And what is your common goal? That is to drink Coca-Cola. Okay, in this covalent bonding, it's just the same as my illustration. The 2 atoms, the 2 nonmetal atoms, to attain stability, will going to share their valence electron for them to become stable. And in this example, the HCl or the hydrochloric acid, the hydrogen and the chlorine shared their valence electron. And you can see here that the shared electron is actually connected by a line. This is a bond line called single bond. A single bond because it's only one line. A single bond. A single bond between the shared electrons holds atoms of hydrogen and chlorine together. Because they share their valence electron, they are holding each other with what we call a single bond, a single covalent bond. Another example is how oxygen gas or the O2 molecule is formed. So you can see, if you will try to go back to other slides, you can see that the oxygen belongs to group 6 and it has 6 dots. So 6 valence electron. So for each oxygen atom having 6 valence electrons, it needs an additional 2 valence electron to attain stability, right? Because 6 plus 2 is 8. And that is true in the case of this 2 oxygen atom. So here we have the first oxygen atom has 6 valence electron represented by the dot or the Lewis dot symbol. So it needs to share with the 2 valence electron of the other oxygen atom to become or to have 8 valence electron. Now, on the other hand, the other oxygen atom needs to share also with the 2 valence electron of the other oxygen atom to attain also the stability or having 8 in order to have 8 valence electron also. Thereby, or that's why this 2 oxygen atom attain stability because they already have 8 valence electron because of the sharing they did. And you can see that the shared electron is actually connected by a line, a bond line. And this is double bond. So the double bond between shared electrons holds 2 atoms of oxygen together to form molecules of oxygen gas. And another example is the nitrogen gas. The nitrogen gas molecule is formed by the 2 nitrogen atom having 5 dots, meaning it has 5 valence electron, and the other nitrogen has also 5 valence electron. So it needs an additional 3 valence electron to become stable or to attain the rule of 8 or having 8 valence electrons. See, because 5 plus 3, that's 8. So each nitrogen atom here in this example needs an additional 3 valence electron. So a triple bond exists between the shared electrons of 2 nitrogen atoms. So take note that each bond represents the shared electron between 2 nonmetal atoms. The bond can be single bond, a double bond, or a triple bond. Now, let us go back to organic chemistry. The term organic literally means any substance obtained from a living sources. So paper, for example, the paper we are using is an example of organic substance or organic compound because it was obtained from a wood pulp, from a paper tree or any other tree that was or that is actually used in manufacturing paper. Charcoal or the uling is an organic compound or an organic substance because it is from the wood from a tree. A fertilizer is organic if it was obtained from decomposed animal manure, a plant part such as leaves or the twigs, or fruits and vegetable peelings. So what is present mostly in living organism that becomes the source of organic compound? The answer is carbon. No, carbon. Why is carbon important to living things? So carbon is most important element in living things because of its special properties. Later we will talk about the special property of or properties of this carbon. Most living things on earth are made of carbon. Living things need carbon the most in order to live, grow, and reproduce. Also, carbon is a finite resource that cycles through the earth in many forms. Why is this important? This makes carbon available to living organisms and remains in balance with other chemical reactions in the atmosphere and in bodies of water like ponds and oceans. Carbon is the basic building block of life. This is the reason carbon dating is effective. All living organisms contain carbon. Also, carbon is so important to life because virtually all molecules in the body contain carbon. Say for example, sugars, the DNA, the proteins, and fats, of course, except water. Because water is only made from hydrogen and oxygen. Carbon can bond to 4 other groups around it and to other carbon molecules. For this reason, it can form long chain molecules, each with different properties. Carbon is important to living things because much of solid portions of life forms are made up of great amounts of carbon. Living things breathe out carbon dioxide. The tree absorbs the carbon dioxide and turns it into oxygen through photosynthesis. And here, we can also see an overview of the carbon cycle. We can see here how carbon is being recycled in the earth, in the different parts of our earth, in the atmosphere, in the lithosphere, in the hydrosphere. We can see that carbon is continuously being recycled from one form to another, converted in different forms, transferred from one organism to another in different forms, continuously. So carbon is always present in nature because of this, what we call a cycle. So now you already have an overview of how important the role of carbon in studying the organic chemistry. Because carbon is present mostly in the living organism. So, for now, we will end our lesson in this part of our lesson about the introduction of the subject organic chemistry. I hope that you have now an insight or an idea of what will be the organic chemistry all about. For the next meeting, we will start talking about hydrocarbons, the different types of hydrocarbons, the aliphatic and the aromatic hydrocarbons, and all other terminologies and lessons about the organic chemistry. So before we end, I would like also to invite you to constantly visit our Google Classroom, because this coming Saturday, as you open your account in our Google Classroom, you can see there the posted questions. It's a kind of of a evaluation test of the concepts, the terminologies that we discuss. So you are going to answer that in a one whole sheet of paper. I want you to write your outputs handwritten. I want you to write your outputs, every activity, every exercises or a test. I want you to write that in a long bond paper, handwritten. So you need to answer those exercises, activity sheets in long bond paper. Then, after answering those questions, take a photo, take a picture of your paper, and then post it in our Google Classroom for checking. Okay? So, thank you very much for your time listening to our first lecture session in this subject. And see you next Monday. It's the same time, 5 to 7 in the evening, our lecture time. And for another video lesson in our subject, Organic Chemistry. Thank you very much. Good evening. Have a pleasant day. And God bless.